All right. So today we're going to start to get into the material where Microsoft Excel is a pretty good tool in order to do the calculations, especially when there's lots of years. You can save quite a bit of time with Microsoft Excel. So I'm going to do a demonstration today, and then I'll ask you to bring your laptop computer to class starting on Wednesday, and we'll use it. Oh, today's Wednesday. Next time on Friday. And we'll begin to use the laptop computers for most of the rest of the semester. So it's best if you have the desktop version of Excel installed. You know, there's both Excel that you can do through the web browser and then also the client or desktop version. There's a couple of tools that are only available in the desktop client version of Excel. So if you absolutely can install it on your computer, then the web-based version is better than nothing, but for the rest of it, it's best if it's installed. So then homework 3 is due next week by 1 o'clock. We're going to go over a few things in class today that could enable you to start working on those problems. And today we're going to be covering some topics that are included in Chapter 4 of the book. And I'll just put in another plug that it's really a great habit to review the textbook discussion that's covering the topics that we address here in class. That just the single exposure you'll get to these concepts in class probably isn't enough to understand and retain them in the way that you really need to. So I really will encourage you to, if you haven't already, get the book, but if you do have it, make good use of it. So review Chapter 4 after today's class. So does anybody have any questions related to the announcements or what we're going to be covering today? No? All right. Now, last time we were in class on Friday of last week, we had this gradient. And I'll be talking about so-called strategies as we look at more complicated cash flow diagrams. And what I mean by that is you need to employ certain steps in order to get money from the future to the present, or whatever the problem is asking you to do. If the amounts are already at the present and it's asking you to find the annual equivalent of that, sometimes it's going to be a multi-step process, and so it's a good idea to try and outline what your solution strategy is before you actually start crunching the numbers. So the idea is you kind of put together maybe like an outline of what your step A, step B, step C is going to be, and then you begin running the calculations in order to execute that strategy. So here we had a cash flow diagram that had two different things happening on the same figure. There was there was an annual series and there was a gradient. And so the best thing to do is to split it apart into those two components. And then the way that we found the overall total present value of this combined annual series and gradient is to find the present of each of the components. So we found the present value of the annual series. We could do the factor table, or you could use the equation method depending on what interest rate's given. And then to find the present value of the gradient and then combining them together. So that's just a refresher of the idea of multi-step strategies. And when we start using Excel, it'll enable us to kind of brute force approach a lot of complicated cash flow diagrams. But then there will be some of them that I'll ask you to do by hand where you'll have to think in multiple steps. So any questions about this particular cash flow diagram and looking back at the in-class exercise we covered last Friday? All right, now what about this one? We can see that there's a gradient here, but it doesn't follow the usual pattern where, remember, the form of a gradient is that in year 1 there's 0g, and then in year 2 is the first time you see the effect of the gradient. So you'll see the gradient amount accounted for in year 2, then in year 3 is 2g, and so on. That's what we saw in this one. So year 1 there's no gradient. Year 2 there's 1 times g. 2 times G, and so on. So is this still a gradient if the amounts are shifted in time towards the right? Yeah, this is still a gradient, and I could still conceivably want to know what's the present equivalent of this amount. You know, what's the economically lump sum value in the present that's equivalent to these amounts over time. So in order to find that, using the gradient factor table, what we'd have to do is break it up into a couple of intermediate steps. The first is the idea that year 3 is going to be kind of our quasi-present. That if we did an operation that's find P given G, it would find a single lump sum value in year 3, and then we could take it from year 3 to the actual present at time 0 with another find P given F type operation. So the solution strategy, the gradient strategy here is, first of all, find the present value of the gradient in terms of a lump sum at year 3. So if you use find P given G, it'll give you a lump sum, but it's not going to take it automatically to year 0 as we understand year 0 to be. Like, the form of a gradient is that it always takes the lump sum 2 years prior to the first time the gradient was observed. And so we're seeing the effect of the gradient here in year 5. So if you do a find P given G, it's going to give you a lump sum amount in year 3. And then as a second step, you'd need to discount that lump sum value from our quasi year 0, which was actually year 3. So you'd have to discount it 1, 2, 3 years to the actual present using find P given F. So that's an example of like a multi-step operation where we can still use the factor table for find P given G, but we also have to apply find P given F. So it'll be pretty important for us to really be meticulous in using that summary convention that's in the brackets. And so we'll get into some detailed cash flow diagrams moving forward. Does everybody still have this interest factor table that I gave you? I think maybe last week or the week before. We're going to use this a lot in the coming weeks. And some of these formulas are built into Excel, and some of them we'll have to type in ourselves. But be sure that you keep this handy as you bring your laptops. We'll also need the factor tables. All right. So this little photo of some rocks at the beach is meant to just serve as a visual reminder of an idea. And the idea is that sometimes we don't know the interest rate. Sometimes the interest rate is the unknown. Like, so far I've always been giving you the interest rates, and then you had to find the present equivalent of, let's say, an annual amount. Or you're finding the future value of a lump sum present value. And you're just using the given I. But there are other times when you don't know I. And in a lot of the analyses we do, the unknown interest rate that you're solving for is an interest rate that brings balance between the inflows and the outflows. So these pictures have nothing to do with engineering economy. But it's just to remind you of the word balance, because when you're solving for the unknown interest rate, what you're looking for is some interest rate that maybe would cause a project to be justifiable. Like, if you're making a lump sum investment today, let's say that you're upgrading some equipment in your factory, and it's going to cost millions of dollars to do it. And the justification for that would be that in the future you're going to be earning some additional revenue. But whether that project is justifiable may depend on what interest rate you have to pay on the money that you borrow, if you're going to be borrowing money for the project. And so whether there is a balance between the amount you're spending now, your investment, and the future profits that you get from that investment, whether that project's justifiable sometimes depends on the interest rate. And so balance just means the present value of the inflows is equal to the present value of the outflows. And the outflows and the inflows aren't themselves always going to be at the present, but if you discount them all to the present, if they're equal, there's some interest rate that makes them equal. So let's take this illustration as an example. What if you had to pay $23,000 now, but by doing that, it meant that you're going to get 6 equal annual payments of $5,000. So how many dollars total are you getting as inflow? Anybody able to multiply? Oh, 30,000, that's right. Yeah, so $30,000 in inflow, and you're paying 23,000, so that sounds pretty good, right? But like, what have you learned about the time value of money? Like, why is it not automatically a yes? If you get 5,000 every year for 6 years, why is it not automatically a yes that you should do this project or do this investment?
Money is less valuable over time.
Very good. Yeah, money's less valuable over time, and so depending on the interest rates out there in the world during this project, it might be that the money you're collecting in the future isn't very valuable and it doesn't justify the project. And so the question is, what would the interest rate have to be? Where's the break point between this project being profitable and not profitable? Or what's the break point between yes, you should do this project, or no, you shouldn't do this project? And by break point, what I mean is there's a certain interest rate where if the interest rates are really high, then these future amounts are being discounted so that their present value is becoming negligible or less significant, so to speak. So the question is this cash flow diagram in balance, and what is the interest rate that makes it in balance? And so we're going to do a quick illustration just to see what is the interest rate that would make that justifiable. And so in this illustration, what we know is the present value is $23,000 and the annual amount is $5,000. So let me just write on the whiteboard here a couple of things. So P is 23,000, A is 5,000, and we don't know the interest rate. And so if we're going to do, remember the equation that is F equals P 1 plus I to the N, but if we have an annual amount, it's a different function that we'd use. We'd say the present value is equal to the annual amount multiplied by find P given A, I equals some interest rate, and N equals 6. So if we're trying to find out what is the present value of these $5,000 inflows, we'll multiply it by whatever factor there is inside of the parentheses here, the factor for find P given A. And so the equation for P divided by A is 1 plus I to the N minus 1 divided by I times 1 plus I to the N power. Okay, so we know that P is 23,000 and we know that A is 5,000. So 23 divided by 5,000 so what is the interest rate that makes all this true? There's if n is 6, that's known, so we can put that value in there. There's only one unknown in this equation. So the interest rate we're trying to solve for is what is the I value that makes 23,000 divided by 5,000 the ratio there. So what interest rate would do it? You can put it in your calculator if you have an equation solving calculator. There are also online tools that we can do that with. There's a site called Wolfram Alpha where it's pretty convenient to type in equations. Let's try Wolfram Alpha. And feel free to follow along if you'd like. I'm not a real pro at Wolfram Alpha. Hopefully we can get it in here. Okay, I'm going to do 23,000 divided by 5,000, arrow key over, equals 1 plus I to the power of 6, to the power of 6, minus 1, and then all of that is all of that is divided by, see if I can maybe paste that in the spot that I need it. There it is. Okay, 1 plus I to the minus 1, and then I times 1 plus I to the power of 6. Okay, so let me just make sure. 23,000 divided by 5,000, 1 plus I to the 6th power minus 1, and then...
It's going to come out wrong. You have to get rid of those parentheses.
Yeah, I don't know why those are there. All right, so I times 1 plus I to the power of 6. All right, so let's have it solve. So compute, we'll think for a moment, and false. That's not the result that I was hoping for. Let me think.
It's interpreting I as the imaginary unit and not a variable.
Yeah.
Okay, so let me just call it x. Thank you. Solve. That's better. Okay, so x is either this negative number, which I know that's not true, or 0.0816. So I is 0.0816. So that's 8.16%. So let me also illustrate in Excel how I would set that up as a spreadsheet. So if I just start Excel here, I've got the present value is 23,000. The annual amount is 5,000. And then the I value, when I start off, I don't necessarily know what the I value is that I'm trying to go for. So maybe I just guess that it's 1%. You know, I'm looking for what is the interest rate that brings balance between the inflows and the outflows. And so what I can do is I can say there's this function in Excel where, by the way, n is 6 years. So there's a function in Excel where it is PV, and so it's asking for the interest rate. I'll just click on this location where I put in a guess value of the interest rate, and then the number of periods, that's 6 periods. I'm going to skip and then in the next field I'll put the annual amount in the payment field. All right. Now, it changes the sign, which we need to talk about that when we get into more detail about Excel. But look what happens if I increase the interest rate from 1% to 2%, 0.02, 0.03. What it's doing is it's discounting the 6 payments of 5,000. Like if the interest rate was 0, then the present value of those future amounts is 30,000. Like if the future amounts aren't being discounted at all. But as I increase the interest rate, what it's doing is it's reducing the value of the future payments. And what I want to do is I want to find the I value that makes the PV of A equal to the known amount of 23,000. So I know that the present value should be 23,000. So the question is, what interest rate discounts these amounts to what I'm targeting, which is 23,000? So is it 5%? Getting closer. Is it 7%? Almost there. What about 0.0816? That's pretty close. Not exactly. Like I'd have to put in more decimals to get there, but that's just an illustration of kind of an iterative process where what you're trying to do is change the interest rate until the inflows and the outflows are in balance. So balance meaning that the inflows and the outflows have an equal magnitude. And of course, we know that outflows is minus from the perspective of we're losing money, inflows are positive. Okay, so if you're trying to find the unknown interest rate, it may be that you've got a cash flow diagram that the problem is just visually summarized for you. And the process that you go through is you discount all the future values to the present, and you use a guess value of the interest rate. If you don't yet know what the actual interest rate is that brings it into equilibrium, you just have to start with a guess. And then you combine it with the amounts that are already at the present, and you keep changing the interest rate until the present value of the inflows and the outflows is equal. So that's the process that was summarized here. Is this is, if we were going to give this a label, this is the present value of the future inflows. But because of a quirk in Excel, it always changes the sign from inflows to outflows. And so that's why it's in red and has the parentheses, is because of the sign that already changes. But if we were going to sum together sum of known present value and discounted future amounts, so then we'd add together the known present value and the discounted future amounts, we're looking for the sum to be equal to 0. So here I could use this tool goal-seek to find out like the exact value. If I want this to be 0 by changing the interest rate, it'll find me a lot more digits. Okay, so now it's actually perfectly 0, and you can see here the interest rate that it found is 8.163782253, etc. So we don't always need all these digits, but it solves for them all the same. Okay, so a little bit about Excel. You've already seen what it does in terms of assumptions. If you use that built-in PV function like I just did, it will find the present value of either a future amount or an annual series. But it assumes that you gave it an inflow and it's going to calculate an outflow. So that's the kind of problem that would be correct for, is if you were trying to find out how much would you have to deposit today in order to make a certain withdrawal in the future. But more often than that, what we're going to want to do is retain the sign of our inflow or outflow. So you're wanting to find out the present value of some future amount, but you don't necessarily want it to change the magnitude like it automatically does. And so to overcome that, what we will do when we're using these functions most of the time is we'll put the negative value in the function. So I'll just say like minus of the amount that's going in, and then it'll retain the sign. It'll retain the same sign as what went in. So if you had positive values in, you get positive values out, but you have to kind of manually correct for that change of direction by putting the minus sign inside of the function. So the negative sign we'll be putting into the formula almost every time we use those built-in formulas in Excel. And I'll remind you of that until it becomes a habit, and it will. Okay, let me distribute this in-class exercise. I've got these handouts. I want you to do this using the equation method. No, let's see. I've given you the cash flow diagrams. Yeah, so you've got the 10% and the, there's two of them there. You've got the 10% and the 12% on here. So use the factor method, and then I'll demonstrate using Excel the solution to this one as well. Got the solution up on the screen here if you want to have a look. So the cash flow diagram is you purchase the equipment, that's an outflow, and then you get $16,000 a year for 5 years, that's an inflow annual series. Net present value means combine together the inflows and the outflows. So when it's asking for the net present value, that means find the present value of the A and combine it with the amount that's already at the present. So I'll give you a moment to finish up those calculations if you're still working through them. Okay, let me show you on Excel how to find balance on this, this first problem, where we're finding the unknown rate. So we know that the interest rate that brings equilibrium between the inflows and the outflows is somewhere between 10% and 12%. And how do we know that? It's because if we discount the future revenue at 10%, then the net present value is positive, meaning those future revenues aren't being discounted enough to bring it into equilibrium. But then at 12%, the future value of the revenue is discounted so heavily that it means the net present value is negative. So it's kind of like a Goldilocks situation. If you have a positive value, it means the interest rate's too low. If you got a negative value, that means the interest rate is too high. So somewhere, the interest rate that we're trying to solve for is between 10% and 12%. So here in Excel, I'm going to just do an illustration of how we could solve this one to find the interest rate. Feel free to follow along if you want. If not, bring your computer on Friday and we'll have some more of these. So here I'm going to put in the interest rate. I'll just start off with a guess, maybe 1%. So this is the unknown interest rate that we are trying to solve for. Start with a guess. Okay? Then I'm going to have the year, amount, and PV of amount. I'm going to make a table where I put in like years through 5, and then the amount that's actually in those years. And so, for example, negative 60,000 was at times 0, and then it was 16,000 in each of the years through year 5. So I'm just making a cash flow table from the cash flow diagram I prepared earlier. All right, now what I want to do is I want to find the present value of the amount for each row and for the number of years it's being discounted. So I'm going to use that PV function that's built into Excel. Equals PV, and I'm going to click on the location of the interest rate. And by the way, I'm going to press a button on Excel that's going to, right now, see how it says B1? That's referring to the cell location where the number is. The interest rate is located in B, column B, row 1. So that's why it says B1 here. That's just, it's like the address of that cell. But if I repeat that formula in other rows, it's not always going to look in that same cell location unless I force it to. So I want to force it to always look in that location for the interest rate by locking the reference. And the symbol for locking the reference is to put in dollar signs. And so I'll put in the $B, $1. So that means regardless of where that function is pasted, always look in B1 for the interest rate. Okay, so that's what the dollar signs mean. So comma, now NPER means number of periods. So that's the year that we're in. So like the 60,000, it's moving 0 years to get to the present because it's already at the present. But then this amount in the next row, it needs to be discounted 1 year to get to the present. So NPR just means the number of periods. Okay, so now comma. So if I put an amount into the payment field, it's going to assume that that's a recurring payment. And the way that I'm handling this cash flow is that each row represents an individual amount rather than a recurring payment. So it's not like there's a bunch of 60,000s. There's only one 60,000. And then in the next row, when I talk about this 16,000 in year one, I just wanted to think of it as a single individual lump sum amount. So I'm not going to put the amounts into the payment field. I'm going to skip over that by putting another comma. And then I'm going to put the amounts into the field that it says here is FV, future value. So minus of the amount. And it's seeing that amount in the future value field, so it knows how to handle it correctly. So I don't particularly like the way that it changes the color like that. I'm going to change the formatting so that it doesn't do that. All right. So when you type in an equation like this, you don't have to type it over and over again. You can just drag down in this. There's this little, it's thicker at the bottom right, that green box there. So I'm just going to drag that down through the rest of the spreadsheet, and it's going to apply the same equation everywhere else. So see, it's the same equation. It's locked to reference the interest rate. Regardless of which row I go to, it's always looking in the same cell for the interest rate because of those dollar signs. But then the reference to the year changes with each row that it goes down, and so does the reference to the amount. All right. So then I want to total everything together. I'm going to create a sum here and find out what is the sum of everything, the net present value. And we've already checked this with 10%. So remember these hand calculations. We found out if the interest rate is 10%, then the sum of the present values is 653. So let me change this to 10%, 0.1. 653. Just like we calculated by hand. Or what if it's 12%? 0.12. Negative 23.24. And that's consistent with when we were using the factor method. So I've got it set up correctly. I verified it by putting in interest rates that I know. But the question is, what interest rate would make this equal to 0? So what is the interest rate that makes the sum of the present values equal to 0? That's a very special interest rate. That happens to be the rate of return for a project. It's like if you put your money into the bank, you want to know what the interest rate is, right? Well, this, we want to find out what interest rate is it that makes that sum equal to 0. So I can try and go find it manually by just typing in a bunch of values until I get progressively closer and closer. It seems like that's further away. 4, yeah, it's getting pretty good and close. 4, 1, closer. 2, very, very close. What about 3? 2, 5. Oh, we're getting awfully close. I can do it that way, which is a little tedious, or data, what if analysis, goal seek, and then my goal is I want, data, what if analysis, goal seek. Okay, my goal is I want this equal to 0 by changing the interest rate. And I tell it, okay, it's going to keep changing the interest rate until it finds the perfect interest rate that makes that sum cell equal to 0. So it's 10.425%. So that is how you can find the unknown interest rate. Or, as it says here in part E, there's a really easy function where you can just do the equals rate function. So equals rate. and look at the things. It kind of gives you like a hint of what it's looking for once you begin a function. So it gives you this hint. First of all, it wants to know NPER. So how many periods are there? There's 5. I'm just going to type in the number 5. 5. Now it's asking, what is the payment? The recurring amount, which it calls a payment, is 16,000. All right, comma. Now it's asking, what's the present value? The lump sum present value that we started with was negative 60,000. Those are all the fields that are required. I'm going to close parentheses. And it says here 10%, but I just need to show more digits of accuracy, and then it'll come up with the same interest rate that I solved for here. So that's the function that's called rate. Okay, so problem 2. Problem 2. Unknown n. All right. So a contractor purchased equipment for $60,000 that provides an income of $8,000 per year at an interest rate of 10% per year. How many years until the investment breaks even? So I kind of step you through that process. I'll pause for a moment so you can think through it, do your calculations, and try and figure that out. And then I'll also show you a demo on Excel how we could come to the same result. Okay, so on the second one, A is 8,000, P is 60,000, and so the ratio of P to A, 60,000 divided by 8,000 is 7.5. So look at this column, the P/A column. What it shows you is how many annual payments are needed to get to a certain threshold of the present value of those annual payments when you're discounting the future amounts at 10%. So you have to have 15 of those to get beyond the 7.5 threshold. So the ratio of P to A is 7.5 between 14 and 15 years. So the way to interpret that is that the break-even occurs in the 15th year. Let me demonstrate in Excel how we could know the same thing. So I'm going to set up a table where I've got an interest rate. This time it's known. The interest rate that we are going to use is 10%, so 0.1. And then we got year, amount, PV of amount, and then I'm going to create a column that's the cumulative PV of amount. Okay, so for the years, I'm just going to go 0, 1 through maybe like 17 years or so. The amount is 60,000 as an outflow, and then the inflows are going to be 8,000 each year. The present value of those amounts is going to be getting progressively lower with each passing year. So what this is showing, for example, is that the 8,000 you get in year 10, the today value of that is only $3,084. But then if you go 15 years in the future, that $8,000 that you get 15 years in the future, it has the same today value as 1915. So it keeps getting lower and lower. Okay, this is the important part, this cumulative PV of amount. For the first year, it starts off as just the present value of the amount. But for each additional year, it is the previous year's cumulative value plus the PV of amount of this year. So what it's showing is that it takes you a certain amount of time to get yourself out of the hole. That you finally break even, like the present value of the amount on a cumulative basis goes positive after the 15th year. And that's consistent with what we found when we were doing it these other ways as well, manually, like with the ratio. So this is an important idea, the idea of a cumulative amount gradually getting higher and higher. This is just when your investment would break even if the interest rate was 10%. It would take you 15 years of operation for that investment to break even. All right, 1:50, we're out of time. Remember that your next homework assignment's available, and bring your laptop to class on Friday.